Hello, everyone. My teammates and I are going to walk you through a capstone project, a system we built called Triage Pulse, which is an AI powered decision support for emergency department triage. It combines predictive models with explainable clinical reasoning. First, the problem emergency department triage is one of the most time critical decisions in medicine. However, we're getting it wrong at an alarming rate. A landmark study of 5.3 million encounters found we were mistriaging about 33% of encounters. That's 1 in 3 patients being mistriaged. Under triage delays critical interventions, and over triage causes financial strain to these hospitals. There have been recent ML approaches that achieve solid AUC scores, yet clinicians are rejecting these systems because they function as black boxes, and accuracy alone is not enough for clinical adoption. So we built our system called Triage Pulse, which addresses both these problems, accuracy and interpretability. It combines 3 things: a fine-tuned fusion model that predicts the ESI triage level, a RAG pipeline that retrieves similar historical cases as evidence, and an LLM reasoning layer that synthesizes everything into an explainable clinical rationale. A nurse is able to use a web application to enter vitals and chief complaint, and the system returns a prediction, the evidence behind it, and an independent clinical rationale. My teammates are going to walk you through the details of the system, and with that, I'll hand it off to Hassan.
Thank you, Boski, for the great overview. Our dataset consists of about 9,000 de-identified emergency department visits from Bet Israel Digonis Medical Center. There are about 22 variables such as vitals, chief complaint, past medical history, and more. Our target variable is the ESI, Emergency Severity Index, a 5-level triage scale assigned by a nurse at the point of care, where level 1 is immediately life-threatening and level 5 is non-urgent. That nurse assigned label is what we are trying to predict. After dropping records with missing triage inputs, we have about 8,000 encounters. We collapsed it to 3 classes, ESI 1, 2, and 3, because level 4 was under 1% of cases, and clinically equivalent to level 3. The chart shows the core challenge. Level 1 is only 6% of the data, the hardest class to learn and the most dangerous to miss. Moving on to our prediction model, our model is a BERT GBM fusion, the dual branch architecture that handles both text and tabular data. The left branch runs the bioclinical BERT on text data such as chief complaint and HPI. The right branch runs tabular data on light GBM for vitals and clinical scores. The key design choice is the probability bottleneck. Light GBM outputs a 3-dimensional probability vector, 1 per ESI class, rather than raw embeddings, forcing it to commit to a calibrated prediction before the 2 branches are fused. The combined input goes through a small fusion head, producing both a prediction and SHAP explanations that surface to the nurse. To discuss our RAG pipeline, it augments the model with real historical evidence at inference time. Patient input is embedded with Amazon Titan Embed and queried against a Pinecone index for past encounters. The top 5 similar cases with their triage levels, diagnosis, and outcomes are pulled and passed directly into the LLM's context as grounding evidence. Critically, this runs in parallel with the SageMaker model call, so it adds essentially no latency. To bring it all together, our orchestration layer is a LangGraph agentic pipeline that ties it pretty well. The nurse submits a case through Streamlit. It hits Fast API, which kicks off the pipeline. 2 things run in parallel. The predict node calls BERT GBM fusion on SageMaker and extracts SHAP attributions, the probabilities from the model. The retrieve node runs the RAG search on Pinecone. Once both complete, the analyzed node passes the SHAP features, the probabilities from the model, and the top 5 similar cases to Claude on AWS Bedrock. which generates a RAG-grounded ESI recommendation and clinical rationale. The LLM reasons over documented evidence first. The ML prediction is visible, but only the primary input. So the system produces two independent signals. That's where the confidence gate comes in. If the model's confidence is 70% or above, we trust it directly. Below that, if the LLM recommends something more urgent, we escalate. The gate can only escalate. We never downgrade a patient's urgency because false negatives on critical patients are far costlier than false positives. The synthesized node then formats the final ESI recommendation for the nurse. Now I will hand it over to Antonio to talk about SageMaker pipeline.
Thank you, Hassan. And now I'm going to show you our SageMaker training pipeline, which automates model training, evaluation, and deployment. The pipeline is flexible because it can be triggered from the CLI or invoked programmatically through Python, which makes it easy to integrate into different workflows. One important feature is caching in S3. If preprocessed data for a given configuration already exists, the pipeline can reuse it instead of running that step again. This helps reduce unnecessary computation and speeds up the overall process. And although here in the training step, the diagram shows one specific architecture, the broader idea here is that the pipeline is designed to be extensible and configurable. At runtime, we can choose hyperparameters, we can select which architecture to train, and even adjust the preprocessing logic when the model requires different data preparation flow via extendable features and the composition. This makes it easy to support new models while maximizing the code reuse through a modular design. And finally, the pipeline keeps track of the current champion model, and after each run, the new model is evaluated against the existing champion, and we only deploy the new model if it performs better than the current champion model. That way, deployment is tied directly to measurable improvement. Okay, so now I'm going to show you a quick demo of our application. Our app is called Triage Pulse. And let's assume here that the primary user is a triage nurse in the emergency department of a hospital. After receiving a patient, the nurse would enter some patient information that would help us identify the patient, including age, sex, and perhaps as we enhance the application, we would add more fields. The user here would enter the triage notes, and here we would enter the chief complaint and any other relevant information for this case. We also want to capture vitals such as heart rate, respiratory rate, blood pressure, and oxygen level, etc., and a pain level. And once all of these values have been inputted, then we would be ready to run the triage assessment. So for this demo, we have added a dev-only feature, which lets us pre-fill the values in the form. And okay, so let's test it. So at this point, we are sending a request to the server, which is running inference and also getting context from our RAG setup. So once we get the response back, and we very clearly wanted to sort of communicate what the result is, and that's why we used a color-coded result, communicating the ESI level. So in this particular case, the user is in immediate and critical level. And the model also provides some suggestions as to how to proceed. The chips here show the clinical factors that drove the decision, and these come from our SHAP analysis, so the nurse can see why the model flagged this patient. On the left, the LLM provides clinical reasoning in plain language, and on the right, similar past cases from our dataset ranked by similarity, so the nurse can see how comparable preparations were handled. At the bottom, the technical detail panel shows that what the ML model predicted and what the LLM independently assessed and how the two were reconciled. So with this, we were hoping to show full transparency into the decision. Okay, back to you, Boski.
Thanks, Antonio. I'm going to walk us through our results. Our BERT GBM fusion model on the test set of 839 patients hit 72% accuracy, a weighted F1 of 0.72, an ROC AOC of 0.828, and a macro F1 of 0.666. That's competitive with the published literature. But the number that matters the most is the L1 critical recall, which is 0.46. So the standalone model missed 54% of the most critical patients. In emergency department triage, that is unacceptable. And that's a gap. That's exactly what motivated our agentic layer. When we added the confidence-gated Landgraph pipeline, critical recall jumped from 0.46 to 0.60, a 14% improvement. The macro F1 of the reconciled pipeline declined slightly, but in this case, it's more important to optimize for the L1 critical class than the aggregate performance for patient safety. So the core takeaway is that selective LLM reasoning over a fine-tuned fusion classifier improves both accuracy and interpretability. For future directions, we want to validate prospectively with real triage nurses across multiple institutions. We also want to incorporate a clinician feedback loop so that system improves from real-world corrections. We want to improve the latency of the system through response caching and smaller distilled models. We want to evolve the RAG index to update dynamically, so we are giving the most recent evidence rather than being static. And critically, we want to incorporate bias auditing across age, gender, and race before any real-world deployment. We have a solid start, and we look forward to taking this work further. Thank you for listening.